Hello everybody, this is the notes for Calculus, section 2.5. We just got done talking about exponential functions in section 2.4. Logarithmic functions is what we're dealing with now. So I guess the biggest idea, the biggest connector is that logarithms, they're the inverse of exponential functions. So you know that an exponential function has this kind of graph right here. This is just the graph of a basic 2 to the x exponential function. Logarithms are inverses of exponential functions. And so when you're talking about graphs of inverses, you have this line, y equals x. Okay, I know I'm writing it again, but that line, y equals x. When you have a function and you want to graph its inverse, you take your function and reflect it over that line, y equals x. And so when you reflect this exponential 2 to the x over that line, y equals x, this is the graph you're getting. And this is what the graph of a logarithm function looks like. So by looking at this graph of the logarithm function, when we talk about the domain, and we've talked about this before, the domain of logarithms, as it says right here, the quantity you are taking the logarithm of must be greater than or equal to, just greater than 0, okay? What you're taking the logarithm of has to be greater than 0. So when you look at this graph, you can see this is just a basic logarithm function. What we're taking the log of is x. X has got to be greater than 0, and you can see that in the graph. There is this vertical asymptote at the y-axis. As far as a range, well, this graph continues going on forever. Very slowly, this graph continues going up forever. And so your range, all the possible y values, well, all of them. It takes a long time to get to a very large y value, but you can still get to it. All right, so a logarithm function, how it is written. Log base a of x is how you say that. The base of the logarithm is the same as the base of the exponential function that it's the inverse of. All right, so going between logarithmic expressions and exponential expressions, like I just said, the base of the logarithm is the same as the base of the exponential function. The quantity that you are taking the logarithm of is the answer to the exponential function. But I think the biggest connector is the answer of a logarithm. Okay, what a logarithm of a quantity equals is the exponent. Okay, so when you're making that connection between exponential functions and logarithm functions, the answer to a logarithm is the exponent. A to what power is giving you the quantity you're taking the logarithm of. So when we look at, you can see this example right here, log base 4 of 64. That equals 3 because 4 to the third is 64. So if I did log base 2 of 16, the answer to this logarithm is an exponent. 2 to what power equals 16? Well, 2 to the fourth is 16, so the answer to this logarithm would be 4. And so there is a nice little pattern to this that I always use in my mind when I'm trying to figure out logarithms and trying to rewrite them. What you do is you take your base of the logarithm to this power, and that equals what you're taking the logarithm of. So 2 to the fourth is 16, and that's rewritten exponentially. So it's this little circle pattern. The base of the logarithm to the power that the logarithm equals what you're taking the logarithm of. So it's just that little circle pattern. That's my visualization to connect logarithms to exponential functions. Logarithms have some properties. All of these should be a review for you, but if they are not, then you got to look them over, and these are things that you need to know for this class. So when you are taking the logarithm of, let me change colors here. When you are taking the logarithm of a product, x times y, okay, that is a multiplication there, you can separate that into individual logarithms with an addition sign. You're keeping the same base for both of them, but logarithm of log base a of x times y becomes log base a of x plus log base a of y. The next property, when you are dividing two quantities inside of a logarithm, those separate into individual logarithms, where it's log base a of the numerator minus log base a of the denominator. Log base whatever of 1, that's 0, because any number to the 0 power is 1. So just rewriting that exponentially. All right, moving over to the right side of your screen here. Log base a of a number raised to the power. What you do is you take that exponent that is to the power of that quantity you're taking the logarithm of. That exponent moves out in front. So it's the exponent times log base a of x. So as an example, log base 3 of 9 to the 4th. You could rewrite this as 4 times log base 3 of 9. All right. This next property here, log base a of a. A to what power gives you the same thing? It's got to be 1. So when you're taking the logarithm of a quantity that is exactly the same as your base, the answer to that logarithm is 1. And then this last property here is just a combination of the two above. Take that exponent of r, move it out in front. You got log base a of a, which is just 1, so you got r times 1, which is r. Okay, there's your properties. So now, as an example, it says use the properties of logs to write each expression as a sum, difference, or product of simpler logarithms. What you want to do, okay, this is kind of a complicated one, but it's got all the pieces. We have a fraction. So what we're going to do is separate numerator from denominator. That's where we're going to start. So this equals, when you're having a fraction inside of a logarithm, you're going to take the log of the numerator, and you're going to subtract the log of the denominator. Now, there is no base written here. It is implied that when there's no base written and it's log, it is implied base 10. That's the common base. Our whole number system is base 10. And so it's just so common, we don't need to write base 10. All right, so now what we need to do is in this first logarithm, we have a multiplication. It's a product. So we're going to separate that into log of the first factor plus log of the second factor. Okay, that's that first quantity. Then we have the minus. Now, for this log of y squared, we have an exponent. So we're going to move that exponent out in front, so it becomes 2 times the log of y. And we got the same thing happening in these first two terms here. Log of x cubed, that it becomes 3 log of x. This square root of z, remember the square root is really just the 1/2 power. So we're going to go plus 1/2 log of z. Then we are subtracting the 2 times the log of y. All right, this is the type of answer that we're looking for these kind of problems. And this was a complicated one. This had all of the parts, and so I wanted to go through this. This is what we're looking for. All right, to solve a logarithmic equation, usually what you need to do, looking at these first two examples, it's usually easier to rewrite it exponentially. 9 to what power gives you 27. So this looks just like the example or the problems that you were doing for section 2.4. 9 and 27, they are related. 9 is 3 squared, that's to the power of x. 27 is 3 to the third power. So we have 3 to the 2x equals, there's a weird equal sign, 3 cubed. Equal expressions, equal bases, exponents must be equal. So x is 3/2. All right. For the second example, log base y of 8 equals 3/4. So again, rewrite it exponentially. The base to the power of the number you're taking, or that equals the logarithm, equals what you're taking the logarithm of. So we're just rewriting this exponentially. Y to the 3/4 equals 8. Now this is kind of a weird problem. You know, if it was y squared, you know to take the square root. What we're going to do to solve for y is get rid of this exponent of 3/4 by taking both sides to the power of 4/3, the reciprocal. So when we multiply these exponents here on the left side of the equation, we just get y to the first, which is y, and that's what we're looking for. Now, 8 to the 4/3. If you remember your rules for these fraction exponents, this is the cubed root of 8, because that denominator 3, raised to the 4th power. So we're looking at 2 to the 4th, which is 16. There's our value for y. All right, this will be the last example we do. We got a couple other things to talk about, but we'll do that in class. Running a little bit long on the notes here. So this last example, what you want to do when you have separate logarithms, you want to be able to combine them into a single logarithm. The key thing here is we are subtracting. So going backwards from what we did here, we started with a fraction, we separated that into the subtraction of those two logarithms, log of the numerator minus log of the denominator. We're just going to take this and go in the opposite direction. Okay, we're going to bring this back together as a fraction. So log base 4 of the numerator, which is the first term, over the second quantity we're taking the logarithm of. That equals -1. So now what we're going to do is basically do what we just did in those last two examples. We're going to take the base of the logarithm to this power to equal what we're taking the log of. So 4 to the -1 equals x over x plus 3. 4 to the -1 power is 1/4. So now we got a fraction equal to a fraction, cross multiply. X plus 3 equals 4x. Subtract an x, we got 3 equals 3x. X is 1. All right. That is all. For now, we got a little bit more to talk about in class, but have a great night.